outcomes of random experiments by numbers. So we introduce the concept of random variables. So every outcome of a random experiment, irrespective of whether the outcome is numeric or non-numeric, it is mapped onto the real axis. That means a value is assigned to that particular outcome. So because this is a variable, it will be different for different outcomes. It's called the variable term comes in, and because the outcome is random in nature, it's called random variable. So next we just introduce what are known as probability distributions. Probability distributions actually, they give a description of the probabilities associated with the different values that the random variable can take on. All right. So this description is called probability distribution. This description can be given in a narrative fashion. It can be given in the form of a table, or it can also be represented graphically. Let's start with the discrete random variable. Random variable that can take on only discrete values, not a continuum of values. So they are called discrete random variables. So here the probability that is associated with every discrete value that the random variable can take on, if you just give it in a tabular form, on the left hand column you have the different values that the random variable can take on. On the right hand column you give the corresponding probabilities of the random variable, assuming that particular value. So that is a very convenient way, or it can be just described straight away. We'll see that, or it can also be represented graphically. So because here the probability assigned to every discrete value is given, it is called probability mass function. The probability distribution function under consideration, it's called probability mass function. Why it is called probability mass function? Just by drawing an analogy with, say, a beam is there and certain loads or masses are placed on the beams at discrete points. So this is analogous to the probability, describing the probability values assigned to different discrete values of the random variable. That's why it's also called probability mass function. I have cited one example here. I have already pointed out earlier that one example of engineering example of random variable can be that a certain number of bits are being communicated over a distance, and in the course of communication there is almost inevitable corruption of the bits by interfering noises. So one of the bits that will be transmitted, one or more of the bits, they will be in error. All right. So the possible values here, we are considering the number of bits in error in the next 4 bits that are to be transmitted. So X is the number of bits in error. So what are the values that this random variable can take on? There can be a situation where no bit is in error. So in that case, the random variable is 0. Remember that by hash, I am representing the word number of bits in error. So there can be 0 bits, 0 number of bits in error. There can be one number of bit in error. There can be 3 bits in error, or there can be all 4 bits in error. All right. I am not considering which bits are in error, but merely I am considering the number of bits in error. So that is also important. So based on a model for the errors, I can describe the probability in this way. Probability of X equal to 0, that's an arbitrary example. 0.6561, probability of 1 bit in error, it's 0.2916, 2 bits in error, its probability of occurrence is 0.0486, 3 bits in error, that probability is 0.0036, and 4 bits in error, it's 0.0001. All right. For a well-designed system, remember that the number of bits in error, that will be very low. I mean, the probability will be very high that no bit will be in error. That's what is considered here the highest probability, because the engineer will always design the system in a manner such that no bit ever is in error. So that is the highest probability that no bit is in error. And obviously, the worst possible situation is all the 4 bits will be in error. That is for a very badly designed system. So that probability is also for a well-designed system very small. So that is, it can be seen here. So it's a very realistic values. Hmm. So this is a sort of description of the probability distribution in a narrative fashion. You can also go for what I have considered as the graphical distribution, as indicated here. So this is the graphical distribution. You can see here probability of 0 number of bits in error, it's this one. Probability of 1 bit in error is that one. Probability of 2 bits in error is this one, in this way. So this is a graphical description. This has resemblance with what I have already stated, that there is a beam supported at one end maybe, and these are loads or masses impressed at discrete points. So this figure and that figure, they are very similar. That's why this function of small x, remember that we are representing the random variable by the capital case letter, and by the small case letter we are considering the values that capital X can take on, that are being represented by small x. So Wx, which gives the probability of capital X equal to small x, it is called probability mass function for this particular random variable. So you can write down. If you write down, then the chance of forgetting will be minimal. Writing down will consume time, but even if I find that the coverage is very not very much in a single class, still then I'll prefer that you write down this material instead of simply handing over to you the material. Is it legible, or I may enlarge it? Let me enlarge it.
Yes, sir, done.
স্যার হয়নি, একটু দাঁড়ান।
হ্যাঁ, ঠিক আছে। কোথায় কোথায় আছো তুমি?
স্যার লাস্টের আগের লাইনটা চলছে, px equal to 0
লেখো লেখো
এখানে।
লেখো লেখো, আস্তে আস্তে লেখো। বলে বলো।
স্যার হয়ে গেছে।
So this is what is called probability mass function for the particular example, for the particular random variable. So here we are only interested in the events x equal to 0, x equal to 1, x equal to 2, x equal to 3, etc. Those are the events of interest. What could have been the other events of interest? We'll see just after this. Other events of interest could have been capital X less than 2, capital X less than equal to 2, capital X greater than 3, capital X lying in the range 1 to 3. So those are some of the other types of events that may be of interest. Simply from this mass function, we can obtain the probability of all such events. I hope you have drawn it. So this is an arbitrary uh, example of a beam being suspended from a support. So distance from the support is represented by small x, and these are the loads applied, mechanical loads or masses applied at different discrete points along the beam. As we move on, you'll find that these long texts are not there, so mathematical expressions are there, then it will become easy for you to write down.
একটু পরে যাবেন?
এই গ্রাফটা
না না, so just suppose the loading on a long thin line.
তোমাদের স্পেশাল পেপারগুলো তো এখনো ঠিক হয়নি নাকি? Not yet decided the special papers?
স্যার আমাদের একটা গুগল ফর্ম দিয়েছিলেন বিজেপি স্যার, আমরা ফিল করে
সেটা
দিয়েছি,
ঠিক
বাট
আছে, প্রবলেমটা যেটা হচ্ছে আমি যেটা বুঝলাম যে ওটা তো একটা ওটা অ্যাসাইন করতে গেলে তো একটা মেরিট লিস্ট দরকার, probably of your second year first semester exam. So it is taking time to get the merit list. What will be the range of values that Wx can take on?
So 0 to 1.
Right. Obviously, Wx is Wx is a probability value, so it can take on values in this range 0 to 1. So Wxi is the probability of x equal to xi, and Wxi is greater than equal to 0. If you add up, Wxi is greater than equal to 0, less than equal to 1. If you add up all the values of Wxi, say I can take on values from 1 to m. So if you add up all these probability values, obviously that should be equal to 1. Here, if you add up these values, all these values, if you add up, that will result in 1. So you must be careful to note these properties. They are very simple. But if I just give you a table of a certain Wx for different values of small x and ask you that is this a valid probability mass function? Then if you don't know, if you don't pay attention to these properties, very small things, you will not be able to answer. These are very small things. But still, you will be fooled. Or say capital X can take on 3 or 4 values, or say 4 values or 5 values, small x1, small x2, small x3, small x4, small x5. And suppose the probabilities of small capital X equal to small x1, capital X equal to small x2, capital X equal to small x4, capital X equal to uh, small x5, these are given. All right. So you are asked to find out what will be the probability of capital X equal to small x3, which is not provided to you. So all the probabilities except for one value of capital X that is not provided to you. And you may be asked to find out what will be the probability. So then if you remember this property, you can easily do that. So these are very uh, good questions for MCQs. Have you written it? After the probability mass function, we will consider what is called cumulative distribution function. Our attention is still confined to discrete random variables. So as I was saying earlier, that instead of capital X equal to 0, capital X equal to 1, etc., we might be interested in finding out the probability of this event, capital X less than equal to 3, capital X greater than equal to 4, all these things. So how will you get the probability of capital X less than equal to 3? If you simply, this is actually a union of all these 3 events. So capital X less than equal to 3 means capital X can take on values of 0, 1, 2, and 3. So the probability of capital X less than equal to 3 will be the sum of these individual probabilities. Probability of X equal to 0, probability of X equal to 1, etc. So it comes out as 0.9999. So that could have also been obtained by considering that capital X less than equal to 3 means 1 minus the probability of capital X equal to 4. Do you understand? 1 minus the probability of capital X equal to 4. So that would have yielded the same result. We could add up the probabilities simply because all these events, not 3, 4 events rather. This should be 4. They are mutually exclusive. They don't have any overlap. So that's why we could add up all these events, probabilities of all these events to get the probability of that event capital X less than equal to 3. So often, instead of giving details of the probability values of capital X equal to small xi, people also give the probability value in this way: probability of capital X less than equal to small x. So that is also another way of representing the distribution. When that is the way distribution is provided, we call it the cumulative distribution function. Earlier we had the probability mass function, now we have the cumulative distribution function. So in this sense, just see that if you subtract probability of x less than equal to 2 from probability of x less than equal to 3, that will give you the value of probability of x equal to 3. Because probability of x less than equal to 2 will be equal to probability of x equal to 0, probability of x equal to 1 plus probability of x equal to 2. And probability of x less than equal to 3 will be the sum of all these 4 probabilities. So if you subtract the previous one from this one, then what will happen? All the terms will cancel out, and which one will remain only? Probability of x equal to 3. So just write down these things. So from probability mass function, you can move on to probability distribution function. I mean the cumulative distribution function, and vice versa. Now, if you consider the cumulative distribution function, the probability of capital X less than equal to small x, and assign different values to small x, all right, assign different values to small x, namely 0, 1, 2, 3, and get the probability values capital X less than equal to small x. And then if you plot these probability values against small x as abscissa, what will be the nature of the plot? Do you have any idea? What will be the nature of the plot?
So increasing.
No, increasing I understand. But as for example, in case of the probability mass function, it consisted of vertical lines. erected at discrete values that the probability that the random variable can take on. How will the cumulative distribution function look like? That's what I'm interested in. You are absolutely right. It will be increasing. But how will it look like? In what manner will it increase?
Sir, rectangular hyperbola?
Rectangular hyperbola. Rectangular hyperbola increases.
Uh, no, sir. Sir, parabolic type?
কি প্যারাবোলিক কেন হঠাৎ মনে হচ্ছে তোমার?
স্যার আমার ওরকম মনে হচ্ছে মানে প্যারাবোলার মতন
মনেটা
এটা।
কেন হচ্ছে বলো? একটা তো যুক্তি থাকবে। হোয়াট ইজ দ্য লজিক?
স্যার কোনো একটা জিনিস মানে সেটা ইনক্রিজিং ম্যানার কিন্তু স্ট্রেট লাইন যখন নয়।
It is actually a staircase. It is a staircase plot.
ও ওকে স্যার।
So this is P of capital X less than equal to small x. So it is a function of small x, isn't it? In the sense that if you assign different values to small x and obtain these probability values, and then if you plot it against small x, obviously it becomes a function of small x. So that is usually represented, in our case, we'll represent that, which is the cumulative distribution function, by the symbol capital F with argument small x. So it is the summation of all the probability mass function values for xi such that xi is less than equal to small x. Often the mass function is also represented in this way, pi. So that's why I have written down this summation expression.
স্যার আগের পেজটা একটু যাবেন, ওটা লেখা হয়নি।
আগের পেজ?
ওইখানটা, হ্যাঁ হ্যাঁ এইখানটা। না 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 অতটা না স্যার। স্যার এর পরের জায়গাটা। হ্যাঁ স্যার এইখানটা। স্যার হয়ে গেছে।
এই অবধি লিখেছো সবাই? হয়েছে?
হ্যাঁ স্যার।
So just see here that it is
হয়নি।
represented by capital Fx. কি বাকি আছে?
হ্যাঁ স্যার, লেখা হয়নি। হ্যাঁ স্যার, থ্যাংক ইউ।
So it's either represented by capital F with argument small x. That is an alternative notation. So it is the capital F with subscript capital X, argument small x, means that this cumulative function is related to the random variable capital X, and small x represents the values that capital X can take on. Whether you use this symbol or that symbol, it's immaterial. Same thing. So because capital F, that is a probability value, it will lie in this range 0 to 1. If x is less than equal to y, then this probability fx will be less than equal to fy. Now you must note here one thing, that although we are considering discrete random variables means capital X can take on only discrete values. The cumulative distribution function, it's not defined only for discrete values. The probability mass function is defined only for discrete values, but cumulative distribution function is not defined only for discrete values. It is defined for a continuum of values, all possible values, a continuous range of values of small x. Even in this case, if you refer to the earlier example, there capital Fx is defined also for non-integer values. Although it's true that the number of bits in error can never be integer, still it's defined for non-integer values as well.
স্যার একবার প্রিভিয়াস পেজ যেতে পারবে? 2 লাইন একটু বাকি ছিল।
কোনটা এখানে?
একটু আরো, হ্যাঁ।
যেখানে মিস করে যাচ্ছ আমাকে বলো, আমি হলে বলো।
হ্যাঁ স্যার, হয়ে গেল।
Just referring to example A, that example on the number of bits in error. Say there if you are interested in finding out what is the probability of capital X less than equal to 1.5, what will that be equal to? It will simply be the sum of the probabilities of x equal to 0 and x equal to 1. So it's W0 plus W1, 0.9477. In a similar manner, you may be interested to find out f equal to 2.3, f equal to 3.8, f of 2, f with argument 2.3, f with f evaluated for 3.8, like that. So here I have sketched the cumulative distribution function for that particular example. For any discrete random variable, it will be a staircase waveform. Fx will be of staircase form. I have given the values based on the example A. So there are steps. This is in the form of a staircase. So at every discrete value that the capital X can take on, that means for every value of small x, I mean every value of capital X can take on, there is a jump discontinuity. And what is the height of this discontinuity? It is the value of the probability mass function at that value of small x. So here at x equal to 0, small x equal to 0, it has a jump discontinuity. And what's the value of the jump height of discontinuity? It's the value of W0, which is 0.6561. Here, it has a jump discontinuity. What's the value of this height of discontinuity? It's W1 plus W0, like that. Sorry, what is the height of this discontinuity here? It's simply W1. But the value that it assumes, this value, this value is W1 plus W0, isn't it? X equal to 2. Here, fx changes to a value W2 plus W1 plus W0. Height of discontinuity is W2. In this way, it's continuing. So try to understand what is really happening. The value that the step will assume will depend on the sum of the probability mass function. All right. Here it becomes W0 plus W1. Height of discontinuity is W1. Continues in this way until it reaches 1. Then it remains constant. F 1.5, 1.5 is here. All right. So what will be F 1.5? It is the probability of having x less than equal to 1.5. So it is obviously 0.9477. Next is probability distributions and probability density function, abbreviated as PDF, of continuous random variables. Now, probability density function is simply the derivative of cumulative distribution function. So density function is the derivative of cumulative distribution function. So for continuous random variables, we have the cumulative distribution function. There is no question of having the probability mass function, but there will be cumulative distribution function carries sense only, not probability mass function cannot be there, because the random variable can take on a continuum of values. All possible values over a range, maybe extending from -infinity to +infinity. Now, in engineering practice, compared to the cumulative distribution function, the probability density function, it has, more applications. Rather than cumulative distribution function, the probability density function is the widely used function for probability analysis, probability determination, etc. Have you completed this figure? To introduce the fact, what will be the nature of, to move on from discrete random variable to continuous random variable, I am considering an example, engineering example. Say there is a machine which cuts copper wire, all right, extruded copper drawn into wire. So that wire is cut by the machine into lengths of approximately 5 meters. So it is desired that all lengths will be 5 meters, but because of manufacturing tolerance, I have talked about the variability of engineering systems. All right. The different samples of different lengths of copper that are being produced, they are not exactly 5 meters. Some of them can be 4.95 meters, some of them can be 4.97 meters, some may be 5.01 meter, some may be 5.2 meter, like that. So such a machine is there. It produces a large number of such lengths. Now, using random sampling, a quality control engineer measures randomly collected 50 of these lengths, and it is found by measurement that out of these 50 samples, 50 lengths, there are 4 numbers whose length is 4.95 meter. There are 10 numbers of samples whose length is 4.97 meter, 4.99 meter, 20 numbers, 5.01 meter, 12 numbers, 5.03 meter, 4 numbers. So these results, they are obtained, they are depicted by this plot shown here. So what are the things there in the plot? So this side, the abscissa is length. Just see here 4.95, 4.97, all in meters. And here, this axis, it gives the frequency of occurrence. So 4.95, 4 numbers, 4.97, 10 numbers, 4.99, 20 numbers, etc. So these values 4, 10, 20, they are called frequency of occurrence. If you divide this frequency of occurrence by the number of samples collected, you will get what is known as relative frequency. And because only 50 samples have been collected, the probability value, we have no other way. But if you want to describe the probability value, it will be obtained simply from the relative frequency. But obviously, if instead of 50 samples, the quality control engineer could amass 1,000 samples or 2,000 samples, better would have been the probability values obtained. So this axis is the frequency, this axis is the relative frequency. which is considered to be equal to probability value. So just see here, 4.95 meter sample and 5.03 meter sample, each of them has a relative frequency of 0.08 obtained by dividing 4 by 50. So it's all right, I think. All right. 4.97 meter, there are 10 number of samples. So 10 divided by 50, it's 0.2. That is the probability value. So this is the probability mass function plot, you may say. All right. Now, so these are the values. I have indicated them. 0.08, etc. So what is the sample space here? Capital X could take on values from 4.94 meter to 5.06 meter. Now, this is the probability mass function. Another way we can plot this probability distribution is that if you group the data into sets, say there is one set extending from 4.94 to 4.98 meter, another extending from 4.98 to 5.02 meter, another extending from 5.02 to 5.06 meter, what would have been the new frequency distribution? That type of a plot. All right. 4.94 to 4.98, that is one group. So this group, what is the frequency of occurrence of members belonging to this group? It's 14. Why it is 14? 4.94 to 4.98. That means, oh, that has been considered as a new set. Yes, this one. 4.94 to 4.98. Just 1 minute. 4.94 to 4.98, how many are there? 4 plus 10, 14. So here you have 14 belonging to that group. 4.98 to 5.02, how many are there? 4.98 means this point to 5.02, this point. 32, isn't it? 32. Yes, 32. And 5.02 to 5.06, it's 4. So this is the frequency of occurrence. What's the corresponding probability of groups? The frequencies have been divided by 50. All right. And the probability of these groups, it is obtained as shown here. This group has a probability of 0.228. That group has a probability of 0.64, and this one has a probability of 0.08. Now, if the data is grouped into sets of 4.94 to 4.96, 4.96 to 4.98, that means smaller groups, narrower groups, 4.98 to 5.00, 5.00 to 5.02. How many groups? Earlier it was 3 groups. Now in this case, there are 1, 2, 3, 4, 5 groups. Then what would have happened? This would have been the frequency of groups and corresponding probabilities obtained as relative frequencies. So compared to that group, what has happened, because we have considered narrower groups, it is tending towards a continuous plot. Now, if instead of 50 samples, if the quality assurance engineer could collect a large number of samples, say 1,000, and then considers very small groups, then what would have happened? The histogram, the plot that you would have obtained would have been much smoother. In this way, with the increase in the sample size and decrease in the width of each group, this will tend to a continuous plot. All right. So by considering smaller groups, what do you mean? you are tending towards a continuous random variable. So that would have been converging to a continuous plot. That's what I mean. So write down these things, then I'll proceed. From here. Have you plotted it?
Yes, sir.
So that was separate data, so-called separate data. Now we will group the data and then plot the probability mass function and that probability, that frequency and probability mass function for these groups. Once you have grouped it, what happens? The probability values, they are now defined over a continuum of values of this length. In your section A, so who is supposed to take your other part? Professor Mukherjee or?
Yes, sir. Professor Mukherjee.
Okay. Have you completed writing? I think you have written it. So this is for the grouped data. We have grouped the data into 3 groups. If you split up into smaller groups, it will get smoother, this plot. It is the probability of occurrence of members of these three groups. 0.28 is the probability of occurrence of any member of the first group. 0.64 is the probability of occurrence of any member of the second group. And 0.08 is the probability of occurrence of any member of the third group. See, the probability values add up to 1. We have drawn it, I think. Five groups here.
Sir, could you please scroll up on?
Yes. This one.
Thank you, sir.
Hmm. Have you completed drawing the figure? This type of plot, they are called histograms. So if the sample size is increased further and the group width is decreased, then this histogram will tend to a continuous plot. Now, what will be the nature of this cumulative distribution function? Forget about these groups. From the probability mass function, you can easily obtain the cumulative distribution function, isn't it? And these are the probability values. Probability of capital X less than equal to 5.06, that is 1. Probability of capital X less than equal to 5.05, that is 1. Probability of capital X less than equal to 5.03, that is 1. Probability of capital X less than equal to 5.01, that is 0.92. In this way, I am progressing from the higher value to the lower value. Next, I'll just depict the cumulative distribution function. Probability of capital X less than equal to small x. Those probability are to be plotted against small x. Have you completed writing?
Yes, sir.
So this is the cumulative distribution function. I should enlarge it, I think, because those values are not legible. Now you can see it, I hope. So here there is a transition from 0 to 0.08 at x equal to 4.94. Just 1 minute. You write down these things, then I'll move on to the plot. So that's how the probability cumulative distribution function is obtained, by sequentially cumulating the probability of occurrence of each value. We are moving from the probability mass function to the cumulative distribution function. So at x equal to 4.94, that probability value changes from 0 to 0.08. At x equal to 4.96, it changes from 0.08 to 0.28. At x equal to 4.98, it changes from 0.28 to 0.52. At x equal to 5, it increases to 0.92. At x equal to 5.02, it increases to 1. Then it remains constant, obviously, at that value. So this is in the form of a staircase waveform because it's a discrete random variable. Now, if you consider, if you could measure the lengths, all right, to larger and larger places of decimals, what would have happened? This plot would have tended to a continuous plot, isn't it? It will tend to a continuous plot. So for a continuous random variable, measuring the lengths with higher precision means you are going for all the possible values. Ultimately, you are converging towards considering all the possible values that it can have from this 4.94 to 5.06 or maybe more. So then you are considering a continuum of values of small x. So this will tend to become a continuous, plot. Have you drawn it? So that will be the nature of the cumulative distribution function for a continuous random variable. Monotonically increasing and ultimately tending to 1 as x tends to infinity. So if for a certain value of small x, it's fx, then for another, just if you make an increment in the value of small x, from small x to small x plus delta x, there will be an increment in the cumulative distribution function value by delta fx. So I have considered a particular value of small x as x1. So what does it represent? This value fx1, it is the probability of capital X less than equal to small x1. Fx is the probability of capital X less than equal to small x. Fx plus delta x, this is the probability of capital X less than equal to small x plus delta x. Just 1 minute. An important thing to note here is that, see, the cumulative distribution function gives the probability of capital X assuming a value less than equal to small x. But it doesn't give you the probability of capital X equal to small x. So that probability is 0. Appears to be a strange thing, isn't it? Whereas in case of the discrete random variable, you had probabilities of capital X equal to small x and also the cumulative distribution function capital X less than equal to small x. But here, probability of capital X equal to small x, that is 0 for continuous random variable. How do you interpret it? How do you explain this paradox? Hmm? This is quite important thing. You have drawn the figure, I hope.
স্যার নোটটা একবার এক্সপ্লেন করবেন?
কোনটা?
নোটটা
আরে এক্সপ্লেন
মানে
করবো, আমি এক্সপ্লেন করবো। এটা এই অবধি লেখা হয়েছে কি?
হ্যাঁ স্যার লেখা হয়ে গেছে।
Now this is, I'll consider that later. Now the axioms of probability and their corollaries, if you use them, you can land up with this properties of cumulative distribution function. All right. First of all, the values assumed by the cumulative distribution function being probability values, they lie in this range 0 to 1. If I assume that x can take on values from minus infinity to plus infinity, a continuum of values, then in the limit as x tends to minus infinity, fx will be 0. In the limit as x tends to plus infinity, fx will be 1. If you have two values assumed by the random variable capital X, say one is small a and one is small b, and if small a is less than small b, then the cumulative distribution function evaluated for small a, it can be less than equal to fb. All right. So with increase in the value of small x, the value of capital F can never decrease. It will either increase or remain constant. So it's a non-decreasing function of small x. Non-decreasing, that's the exact term. Note down these properties. So that is valid for both discrete random variable as well as for cumulative random variable, continuous random variable. DRV stands for discrete random variable, CRV stands for continuous random variable. Fx is continuous from the right. It means that Fa is equal to Fa plus. That is the meaning of this statement. Or as I've written here, for h greater than 0, Fa will be limit h tending to 0, a plus h. This is x tending to minus infinity, it's written here. This is x tending to infinity. So if the cumulative distribution function has points of discontinuity, when can it happen? When the random variable is discrete. Under that condition, the cumulative distribution function will be equal to the limit from the right, as revealed by this particular property. Probability of capital X lying in this range A to B is FB minus FA. Probability of X equal to B is FB minus FB minus. So according to this property, probability of X equal to B is given by the magnitude of the jump of the cumulative distribution function at the point B. What does it imply? In case of discrete random variable, only there can be a jump. For continuous random variable, there cannot be such jump discontinuity. So in case of this continuous random variable, the probability of X equal to B will be 0. All right. So as I have stated, this particular statement appears to be a paradox. I will try to interpret. Only interpretation is possible. I try to do that and then stop today. I should have stopped 15 minutes earlier because I have all of us were engaged in this general viva voce for the final year students, but I thought that without addressing this particular thing, that probability of X equal to B will be 0 if the cumulative distribution function is that of a continuous random variable. Unless I do that, it will remain incomplete, the discussion. Now, remember that continuous random variables, they are actually ideal models for what we refer to as continuous valued measurements. All right. So these are just idealized model. They serve as idealized model for what we may refer to as continuous valued measurements. Say, take the case of a measurement by a voltmeter. Let me just interpret it first, then I'll allow you to write. Suppose a voltmeter, it shows 5.127 volts. Because this voltmeter can read up to third place of decimal. And because physical devices, they have limited precision. So the voltmeter shows 5.127 volts. What does it mean actually? It means that the random variable representing the voltmeter reading it can take on values from 5.1 to 65 to 5.1 to 75 volts. All right. So that is the meaning. All right. Because all numbers, all values in this range, x extending from 5.1 to 65 volt to 5.1 to 75 volt, all the values that x can assume in this range, they will be rounded off to 5.127 volts, because these voltmeter cannot read beyond 3 places of decimal. So as such, there is no paradox, because probability of x lying in this range, it has positive probability. It doesn't have zero probability. It has non-zero probability. All right. So that is the interpretation. But you may say that, well, sir, why can't we represent it by a discrete random variable, which can read, which can take on values up to the third place of decimal. That means 0.001, 0.002, 0.003, 0.004. In this way, the discrete random variable can take on values. You may argue that in that way also we can represent the random variable. We can represent the random variable by a discrete random variable representing the voltmeter reading. But think in this way that, well, we have considered that we have a random variable which can take on values, discrete random variables 0.001, 0.002, 0.003, etc. But if we have another voltmeter that can read up to fourth place of decimal, then this particular assumption will get disturbed. Then you have to represent it by another discrete random variable that can take on values of 0.0001, 0.0002, 0.0003 in this way. All right. So that is the problem. So that's why it's better to consider it as a continuous random variable. That is the interpretation. All right. And it's very much mathematically easier to deal with continuous random variable. So that's why this is the situation. So that's a possible interpretation. Now write down. CDF is continuous at point B means that random variable is continuous. Or I should mention this, or it may so happen that the random variable is a mixed random variable. All right. A sum of a discrete random variable and a continuous random variable. And the CDF is continuous at point B means that that region corresponds to the continuous random variable. That can also happen. হয়েছে এই লেখাগুলো?
Yes, sir.
After you complete lighting, let me know. I stop here. Acha, one thing, this is important. Oh, no, you are third year, sorry. Second year.
Yes, sir, done.
হয়েছে সবাইয়ের? So from 22, it has dwindled to 12. ওকে, হয়ে গেছে কি সবাইয়ের?
স্যার
হ্যাঁ, স্যার।
এক্সাম্পল এ যেখানে ছিল ওই জায়গাটা একবার দেখাবেন ওই পেজটা? স্যার এই জায়গাটা পেরিয়ে গেলেন স্যার আপনি মনে হয়। হ্যাঁ স্যার।
অনেক জায়গায় আমি এক্সাম্পল এই কথাটা লিখেছি।
না না এটাই বলছি। স্যার এর পরেরটা একটু তুলুন স্যার এই জায়গাটা। হ্যাঁ স্যার ঠিক আছে।